All right, here we are again. So today we are going to continue our conversation about the Laplace transform, and more specifically, we will introduce the inverse to solve ODEs, and actually that's the whole purpose of introducing this transform in this course. So what I did here, I just copied the number one, the properties we have proven last time. I'm sorry, I forgot to write the general formula for this one, which we proved last time. This is just if you have f prime, but if you have f double prime or triple prime, we proved the general formula. And then we started creating a table of anything we've proven, so you can use it anytime you want, okay? So you can always refer to this, and you can always use these if you want, okay? So we are going to introduce the inverse, and so as we know, this is just an example. Laplace transform of the exponential is 1 over s minus a, so long s is more than a. I drew a little picture here for you to help you. So if your input is e to the at, that's your input, that's your output. So this gets mapped onto this through a Laplace transform. So if you want to go backwards, you have to use the inverse Laplace. So the inverse Laplace of this has to be that, okay? Just like we said, Laplace transform of 1 is 1 over s. Therefore, inverse Laplace transform of 1 over s has to be 1, assuming s is more than 0. And since Laplace transform of 0 is that 0, then the inverse Laplace of this 0 is that 0. Let me just pause here and say a word about this. I meant to mention something about it last time and I forgot. All linear operators, all of them with no exception, they always send 0 to 0. It doesn't mean that the function has to go through 0, 0 at all. You could have a function that obeys the linearity, yet it doesn't go through 0, 0. What this says is if x is 0, y must be 0. So that's why, for example, last time I said something like this. This is not a linear operator because the y-intercept wasn't 0, right? So this function goes through 0, 1. What does that mean? It means when x is 0, y is not 0. Y is 1. Again, it doesn't have to go through 0, 0. But if x is 0, y must be 0. And that is... that's how you recognize linear operators, okay? So keep that in the back of your mind. Now in here I wrote, and I know you know the answer to this, but I want to make sure we don't abuse it, okay? Oftentimes, you know, in your math classes in the past, your teacher would say, you know, if, they'll say something like, if f inverse exists, right? And what they mean to say, what the books mean to say is, it's silly to say if f inverse exists. F inverse always exists. You just go backwards. What it means is for it to be 1 to 1. So when we say if a function is not 1 to 1, we say f inverse does not exist. It's a tradition in mathematics. It's not the proper way to say it, but that's how we do it. Just like when we say the limit doesn't exist. Well, sometimes a limit of a function gives you two values, right? And we say two values, gives you L1 and L2. And then we say limit doesn't exist. Of course it does. You get two of them. You don't just get one, you get two. What it means is the limit is not unique, right? So I would understand if you get infinity and you say limit doesn't exist. But if I get 3 and a 5, well, I do get limits. It's 3 and a 5. I got actually more than one. For the limit to exist, it has to be unique, right? So for a function to have, for an inverse to exist, what it really means, it has to be 1 to 1. And I say all of this because sometimes students do this, students do this. So they say, for example, if x equals y, can you conclude then that f of x equals f of y? The answer is yes, all the time. However, if f equals f of y, does it mean that x equals y? The answer is no. Okay? It would be a yes if the function is 1 to 1. So for example, log of x, if log of x equals log of y, you could definitely say x equals y. Why? W-H-Y. Because the natural log is a 1-to-1 function. Or if you have e to the x equals e to the y, feel free to say x must be y, because exponential functions are 1-to-1. But if you have something like x squared equals y squared, it does not mean that x equals y. We know it's false, because x could also be negative y, right? So think of y equals x squared, and think of 2 and negative 2, and they both produce 4, right? X squared is 4, and y squared is 4. X1 squared equals 4, and x2 squared equals 4, but x1 is not x2, right? It's not x2. x1 is this, and x2 is that. Or, obvious example would be like trig functions. They're not 1-to-1 functions, right? So if I have sine of x equals sine of y, it doesn't mean that x equals y. Typical example would be, let me just build one quickly. Let's use pi over 3. So sine of pi over 3 is the same thing as sine of 2 pi over 3. They both give me, what is it? They both give me half, I believe, or root 3 over 2. Root 3 over 2. But that doesn't mean that pi over 3 is 2 pi over 3. That's not true. That's false. Okay? Even though sine of pi over 3 equals sine of 2 pi over 3, it does not mean that's... in other words, you can't just introduce inverse sine on both sides and so-called cancel. Really, that's not what we're canceling here. What we are trying to say is, if you compose a function with its inverse, you get the identity function. But that is true only if the function is 1-to-1. Of course, if f is 1-to-1, f inverse would have to be 1-to-1, and vice versa. Okay, so keep all of those in mind. I know you know this kind of silly pre-calc stuff, but don't just cancel functions from both sides. Again, you're not canceling, you're actually introducing the inverse to kill the function, to leave the identity. Okay, that's what is happening. So just keep this in the back of your head, okay? So let's move on. Let's work out an example, okay? So here is an ODE. Of course, it's linear. It happens to be homogeneous. The leading coefficients are constant. You can easily use the characteristic equation, solve the quadratic formula, and you're done. And of course, with the initial conditions, you won't have constants. You will get an actual particular solution. This is an ODE. These are the initial conditions, and therefore, this is an initial value problem. So what we want to do today is we want to use the transform to solve the ODE. And I picked a kind of a straightforward one. So what I did is I applied Laplace on both sides. Okay? Now, Laplace transform of the sum is the sum of Laplace transforms. So it's Laplace transform of this, plus Laplace of that, plus Laplace of that. And of course, Laplace transform of a constant something, you can pull the constants out. And that's why I got this, and that's why I got this, and that is obvious. And the transform of 0 is just 0. So the right-hand side is very straightforward. Now, as I said earlier, the general case for this third property, I forgot to write it, is exactly what I used here. Okay? So Laplace transform of y double prime has to be this. Please go back and check to see if I made a mistake. And Laplace transform of y prime is this. According just to that, it's S transform of f minus f of 0. Now, f of 0 happens to be or y of 0 happens to be 2. That's why you have a 2 here, okay? So S, the transform of y minus f of 0, okay? And f of 0 is just 2, it's given. And y prime of 0 here is 3. That's why I subtracted 3, okay? Plus 2 transform of y equals 0. I collected my alike terms. So obviously I'm looking for the transform of y so I can solve for y. So I collected this and this and this and I factored them out. You get s squared minus 3s plus 2. And then the leftover minus 2s minus 3 minus 2s minus 3 plus 6 and nothing here equals 0. So I took all of this to the right hand side and divided by this. I got that. Okay? This is 3. 3? Yeah, minus 3. Yeah, good. It's correct. I thought I made a mistake. So now, when you get to here, there is nothing in this table on the right hand side that gives me this. So of course, what we need to do is try to make it look like something like this, right? Or 1 over s minus a quantity squared or something of that sort, or some sum of squares, okay? So what we do here is we factor the bottom. And if you use partial fractions, and I hope you remember how to use partial fractions, this is linear, you just get a constant, and this is linear, you just get a constant. Basically, we want to split this product, because this product does not happen. You just never see a product at the bottom. So we had to split it, okay? We have no choice but to split this. And I call this A and B, and I cross multiply. You basically do this times this, plus this times this, and force that to be 2s minus 3. The bottoms will be the same, okay? I got 1 and 1, and I verified it. S minus 2 plus s, that's 2s minus 1. Minus 2 minus 1 is minus 3. Yep, 2s minus 3. So we know we're correct here. And now this is familiar, and this is familiar. So if you look here, I'm going to apply the inverse transform on both sides. Okay? So that gives me y, right? It's going to give me y, and you're going to get Laplace of this sum. Now, the inverse of that sum. Now, the transform inverse of the sum is the sum of the inverses, right? That is something I'm going to ask you to prove. Now, we know this is a linear operator. How about this one? Okay. It turns out to be true, which we need to prove for homework. And that's why I used it, but don't take it for granted until we prove that the inverse of Laplace is also a linear operator, which means the inverse Laplace of the sum is the sum of the inverses. Now we know what this is, and we know what that is just based on this, right? A, so that's going to be e to the 1t, and this is going to be e to the 2t, right? So since we know that this is true for s more than a, we know Laplace of e to the t is this, and therefore e to the t is the inverse of that, which is exactly what I'm looking for. The same thing here, and therefore here are my two functions, and done. Okay? So now, what I would like you to do, so again, the assumption we're making from this example number 1 is that this is a linear operator, and we need to prove it, okay? The second problem I want to do, I didn't want to do all the math. I didn't want to give you this. I just went straight to the inverse. And the question is, how do we find the inverse transform of this quantity? Okay, we need to split it. But I'm going to make use of a rule that we haven't proven either. And also I'm going to ask you to prove this for homework. Notice, let me pause here. Notice we have e to the at times some f. So you could call this, let me remind you what the question is, Laplace of power and exponential. This is what I'm introducing right now. I'm just giving you a hint basically. You can call this the power, the t to the n, and use that. Or you can go here and call this e to the at and use that. Okay? These two will not help you because they are separate, and I'm looking for Laplace of the products. I'm looking for Laplace of the products. So these two will not help you separately. We know what each one of them is, but we don't know Laplace of the products. And you have no right to say that Laplace of the products is the products of Laplace, okay? So you would need to either use 2 or 4, okay, for your homework. And so I'm just going to give it to you here. It happens to be n factorial over s minus a to the power of n plus 1 to be proven. And I notice quickly that a must be 1. So it's easy for me to know that this piece has to be e to the t. Then the question is, I need n factorial. I have 4. If I use 4 factorial is too much. 3 factorial is also too much. So I use something smaller than 4, which is 2 factorial. So if I have 2 factorial, that means n is 2, then I plug in 2 here. So I'm getting closer now. So it looks like this is the function I'm going to use. Laplace transform of t squared e to the t is 2 over s minus 1 cubed. But I have 4 over s minus 1 cubed. So that's easy to do. You multiply by 2 both sides. Okay? So that's what I did here. Now you've got to be careful. Now you are used to say this. Laplace transform of CF is C Laplace transform of F. But you're not used to going backwards. So when I see a C Laplace transform of something, I can insert the 2 inside. Because I'm going to take inverse of Laplace, so I cannot have this 2 here. It has to go in. So that's what I did. I put 2 inside and then apply inverse Laplace on both sides. So that gave me if I put the 2 here and apply inverse transform, I'll get 2 t squared e to the t. Here it is. I should have written it on the left-hand side. And this one will be the inverse of 4 over s minus 1 cubed, which is exactly what I want. I want to compute the inverse transform of this. So this is your answer, okay? I didn't want to give you an entire ODE. I just went like halfway through. So if it doesn't look like one of these, you just have to be creative and slow down until you pull it, okay? And let me conclude with the third example, and I'm doing this for a different reason. And then I'll give you your homework, okay? So this is a short video, I hope. Of course, I know you know how to solve this, right? The homogeneous piece is y prime minus y equals 0, so that has to be e to the t. And then the particular one, you're going to say a linear combination of sine and cosine. So it's going to be a cosine plus b sine, and you solve, and you get the values of a and b. So most likely it's going to be e to the t plus some sort of cosine plus some sort of sine. Okay, this is just based on what we did in the past. Once again, I gave you an entire initial value problem, but I'm doing this for a different reason because you may have forgotten how to deal with partial fractions for certain situations. So apply Laplace on both sides of the equation. Laplace of the difference is difference of Laplace, and the 2 can come out, okay? Now, based on one of the properties, we know Laplace of y prime is s Laplace of y. I don't know if I said ln. I didn't mean to say that. Minus y of 0. And y of 0 is 0. So that's going to disappear completely. And that just stays. Now, so I just gathered my pieces. So you get the transform of y parentheses s minus 1. That's gone. That's 0. Okay? Equals 2 over this. Now, I wrote this as s squared plus 1 squared to remind you that this reminds me of the Laplace of the sign has to be, Laplace of the sign where beta is 1 has to be 1 over s squared plus 1 squared. So that's why I wrote it that way, so you know where it came from. And of course, this is just 1 over s squared plus 1 times 2, okay? Divide by s minus 1 and get this. So this is what you may have forgotten on how to split this. Earlier, we had s minus 1, s minus 2, and I put a constant over s minus 1 plus a constant over s minus 2. Now I have a quadratic, okay? And when you have a quadratic, you want to think of a linear piece. I don't want to call it bx plus c. I call it bs plus c because my variable, my output is always a function of s, okay? Now, if I had here, let's say, quick review, if I had s minus 1 squared and some constant here, the way you split this, you do constant s minus 1 plus constant again, even though it's quadratic, okay? And then you do s minus 1 squared. If you have s minus 1 cubed, you do this plus this plus this. Okay? But that's not what we have here. What we have here is we don't have a perfect square or a perfect cube. We have a quadratic. And for a quadratic, for it to work out for you, you need a linear over quadratic, because that helps, you know, like, especially with the integrals, you get natural log. Okay? So what I did is I did this times this plus this times this must be 2. I collected my alike terms. Here you go. I called 2 0s squared plus 0s plus 2, and then I lined up my numbers. A plus b must be 0, c minus b has to be 0, and a minus c has to be 2. I quickly noticed that I can add these two and say a plus c is 0, and then I copy the bottom one, and then I add them up again. I got 2a equals 2, which means a equals 1. If a equals 1, c is negative 1 because they're opposites. And then I use the first equation here. If a is 1, then clearly b has to be negative 1. And therefore, Laplace transform of y is a, which is 1 over s minus 1, here it is, plus negative s minus 1. So the negative s minus 1 over this, I split it. So I had this, kind of went a little fast. Negative s minus 1 over s squared plus 1. I split it right there. So I wrote negative s over s squared plus 1 plus negative 1 over s squared plus 1. But I didn't like to have a plus. I just put minus minus, right? That's a minus, and plus minus is a minus, okay? And of course, these are famous, right? So y has to be the inverse Laplace of this minus inverse Laplace of that minus inverse Laplace of this, okay? That is an e to the t, because a is 1, so e to the at, so e to the 1t, minus, now that is definitely a cosine, so the cosine of beta t is s over s squared plus beta squared, so I get the negative cosine of t, and this one is negative sine of t. Notice sine has a constant at the top. Sine has the constants at the top, beta. However, the cosine has the actual variable s. That's why it stayed. That's why this is the cosine and this is the sine. And that is exactly what we expected. We said for the homogeneous, you get e to the t. And for the particular solution, you're going to get a combination of cosine and sine. So that works out really well, okay? So this is kind of a not too hard of a presentation. I'm going to conclude with the assignments. The first thing I would like you to do is prove that the inverse Laplace is also a linear operator, because I used it quite a bit today, okay? I also would like you to prove that Laplace of this product is this. This is completely new to you, okay? Again, feel free to use this or use this, okay? And finally, not finally, I would like you to find the inverse Laplace of this quantity. So find a way to split this, and I just gave you a hint when you have a perfect fifth, right? So be careful with this one. And then from your book, I would like you to do 2 problems only. So you have 6 of them, okay? 5 problems, okay? 1, 2, 3, 4, 5. I want to conclude very quickly with a comment, which is, remember that these are all of exponential order, and they're all continuous. And that's why you can take Laplace of those functions, okay? Why are they of exponential order? Clearly, t to the n is a power, and it's always less than CAT, right? Of course, it is bigger than its negative. So t to the n is of exponential order, and it is continuous, and therefore the Laplace exists, which means the integral of e to the minus st f of t dt from 0 to infinity, this integral converges. It exists, okay? The same thing here for sine and cosine, okay? We know for a fact that sine and cosine, they're all between -1 and 1, right? So so clearly one is less than CE to the AT and vice versa. Okay, so they're also of exponential order. Okay, so be careful. You can't just use Laplace on anything. Laplace doesn't have to exist. A typical example, I'll give you one example actually, where the Laplace doesn't exist, because I can guarantee you that the integral is not going to converge. And you may want to give it a try. If you look at this function, let's say my function is, let's say, this, okay? This is not of exponential order. So we know that if you do this, you're going to have a problem. This integral does not exist. Does not exist. Why? Because this is not of exponential order. Okay? So that's just a quick comment for you. I hope you found it useful, and I will see you next time.